something like 4, 2, 1, 1/2, 1/4. Okay, can you tell me what's the next number?
1/8.
1/8. What are we doing?
Splitting in half.
Yeah, we are always dividing by halves, right? So 1/4 divided by 2 will give you 1/8, and if you divide this again by 2, you get 1/16, something like this. And in the previous examples, we looked at the differences, right? For k squared or n squared or n cubed, we were looking at the difference and finding patterns from the differences. That's how we were doing it. Here, it's not the differences, but everything has the same multiple of the previous one. So it's always times 1/2 to get to the next one. Times 1/2, times 1/2. And any sequence that proceeds in this fashion is called a geometric sequence. And if you add up the sequences, you say it's a series. Okay, so the difference between a sequence and a series is sequence is just individual numbers, where series means you add them up. Okay? So in general, a geometric sequence has the form. You start from some number a, and then you keep multiplying by some common ratio r. Okay, and let's say you do it until n minus 1. Now you might wonder why I stopped at n minus 1. The reason for that is because I can rewrite a as a times r to the 0th power. And if you do that, everything looks like a times r to some power, where the power goes from 0 to n minus 1. And only when you go from 0 to n minus 1, you have n terms. Okay? That's why I stop at n minus 1, not at n. And the geometric series is the summation of these things. Okay? Now let's try to think about how to write this in sigma notation. Okay, so what's common is that every one of these, even this one, if you think of it as a times r to 0th power, every one of these look like a times r to something, right? Something. Now, what should I put in here so that when k is 1, this will be 0, and k is n, this will be n minus 1. So, okay, let me, since that one's confusing, let me ask you the following. What if I put n minus 1 here? What would this produce? This is going to be equal to, what's the very first term? When k is 1, what does this evaluate to?
AR.
AR to the n minus 1 when k is 1, okay? When k is 2, again, you get this. Because this has no k in it, so it never changes. It's always this, right? So you just end up adding AR n minus 1 n times. That's what this does, okay? Only when you put k, that k is going to change as you change the value of k, and it's going to produce all of these. Is that good? All right. Okay. So this is the series that we want to learn, okay?
Wait, Tom?
Yes.
I got one more question. So how would the AR k minus 1 produce just a?
Oh, when k is 1, what happens? You have 1 minus 1,
Yeah, so
which is 0.
yeah.
What's r to the 0th power? Anything to the 0th power is
0.
1. No,
Oh,
anything
one.
to the 0th
Oh,
power is 1. Yeah, yeah.
Okay.
So 2 to the 0th power is 1, 3 to the
Yeah.
0th power, everything to the 0th power is 1, therefore a times anything to the 0th power is 1, so you just create a.
Oh, okay.
Okay? Right.
Yeah.
Okay, so now I want you to know the formula for this guy, how to get that. And to do that, I need to teach you a factorization formula that is sometimes taught in the algebra course, but not many. All right, so the formula that you have to know in order to understand this is the following. If you have x to the n minus 1, it factors as x minus 1 and x to the n minus 1 plus x to the n minus 2, all the way down to x plus 1. I don't think anyone here would have seen it because it's like for competition math. It's algebra, but it's competition math algebra. So not many of you have seen it. However, you may have seen the following one when n is 3, because that's not so hard. So n cubed minus 1 factors as x minus 1 times x squared plus x plus 1. How many of you have seen this one? Do you remember seeing that one? You've seen it? Have you seen this formula, the second one?
The second one, yeah.
Yeah, right? So this one is exactly the same as this one if n is 3, right? Because 3 minus 1 will give you 2, and then you just keep going down, right? Yeah. So you can kind of, just from this, you can kind of accept, oh yeah, in general, if you have like x to the 5 minus 1, this is going to be x minus 1 times x to the 4th, x to the 3rd, x squared plus x plus 1. That's going to be true. And it's not that challenging to check this factorization. You might think, oh, that looks really scary, but it's kind of obvious if you actually do the computation. So let me show you why. So let's say we didn't know this, and somebody said, can you check that this is indeed same as that? And checking is easy because, you see, if I do this, then I get x to the 5th, x to the 4th, x to the 3rd, x squared plus x, right? But then now you have minus 1 for everything, which is minus x to the 4th, minus x cubed, minus x squared, minus x, minus 1. And now you see a huge massacre happening. They kill each other, right? And the only survivors are what? Exactly this, right? Yeah. So you can kind of see what's happening here. If you have x minus 1 multiplied to this, only the very highest order term, x to the n, and the lowest term, which is negative 1 times 1, survives after everything in between canceling, if you did the FOIL thing. That's why this is true. Are you convinced? Is that good? All right. So if you accept that, then here's how we go about finding finding out what this is. Okay. So now we do summation of k equals to 1 through n of a r k minus 1. I'll just erase this for now. And it's a straightforward calculation. When k is 1, what does this produce? A, just A. When k is 2, this produces AR, and then AR squared, all the way up till when k is n, what does this produce? A, R, n minus 1, right? And now we are going to factor the a out. And you have that, right? Wait, that's exactly like this part, except that instead of instead of x, I have r, and it's just written backwards. Do you agree? It's exactly the same thing, it's just written backwards, right? So what I can do is, I can just invent a r minus 1, because that's what makes it like that, okay? But there's no free lunch. Whenever you multiply something out of nowhere, what do you have to do? In order for this equal to be preserved, you have to divide it by the same thing again, okay? Then there's no harm done, right? But now we can simplify the top. What is that? This formula here, right?
It's the whole thing.
R to the n minus 1 over r minus 1. Okay? Now, let's try to use this formula for the previous sequence that I've introduced. So example 1, let's say you have 4 plus 2 plus 1/2. So, what's a? A is the initial term, right? 4. A is the initial term. What's r? R is the, what do we call r again?
Ratio?
Common ratio, right? So ratio is what?
1/2.
1/2. What about n?
6.
No, 7, because there are 7 terms, right? So n is the number of terms.
Oh, you do 1/6.
1, 2, 3, 4, 5, 6. Oh, sorry.
16.
It is 6. Okay. That's number of terms. Yeah, the previous example I did over 16, right? Let's just keep it this way. Then I can use either of these formulas. They're both good because I can multiply -1 top and bottom to turn this one into that. You usually use this one when absolute value of r is less than 1, and you usually use this one when absolute value of r is bigger than 1. So if I plug everything that we figured out into this formula, then you get 4 times 1 minus 1/2 to the 6th power over 1 minus 1/2, which is 4 times 1 minus 1 over 64 divided by 1 minus 1/2 is just 1/2, right? But dividing by 1/2 is same as multiplication by 2, so it's 463 over 64 times 2. Dividing by 1/2 became multiplication by 2. 1 is equal to 64 over 64, so this simplifies to that, right? And then finally you get, if you cancel these out, 64 is 8 times 8, so you get 63 over 8. Okay? So that's what you get, and you can check by direct calculation as well. I mean, if you put everything over 8, it would be 8 in the denominator. That would be 8 times 4, which is 32, plus 16, plus 8, plus 4, plus 2, plus 1, right? And then if you keep adding, you'll see that the top one gives you 63. Right? So that's how you do the geometric series.